Let's add another fundamental interaction to the list that we can describe and use to predict motion using Newton's second law. Beyond gravity, there's a second major category of fundamental interactions that includes electric and magnetic interactions, the strong interaction, which causes protons and neutrons to stick together in atomic nuclei, as well as the weak interaction, which plays a role in certain processes such as the decay of free neutrons. We're going to focus on only one aspect here, the electric interaction that arises between objects that have the physical property of charge. We'll start by taking as our system an object with a total charge we'll take to be Q2. Since this is the first time we've talked about the property of charge, let's state here some key facts. Charge is a scalar quantity, and for a given object, the total charge can be zero or non-zero. For this example that we'll discuss, we'll assume the objects will have non-zero net charge. That non-zero charge can be positive, like it is for a proton, or negative, like it is for an electron. Now, charge is a fundamental quantity, which means it has its own physical dimension with the corresponding unit called the Coulomb. Now, if there is in the surroundings another object with non-zero charge Q1, the system experiences an electric force along the line between our system and the object in the surroundings, such that either the system is attracted toward the object in the surroundings if Q1 and Q2 are opposite charges, that is, one charge is positive and the other is negative, or the system is repelled away from the object in the surroundings if Q1 and Q2 are like charges, that is, the charges are either both positive or both negative. We'll discuss how to handle these different cases shortly. Regardless of the case, we'll give this force the symbol F subscript E onto by 1, which is shorthand for the electric force on our system with charge Q2 due to the object with Q1 in the surroundings. Now, to specify the direction of the electric force, it's clear we'll need to account for the positions of the objects in a manner similar to the way we had to handle the positions of two masses when we discussed Newton's universal law of gravitation. So, as before, if we make a choice of origin for a coordinate system, then, once again, we can define the relative position vector r that is parallel to the line joining the objects. The vector r locates where our system, charge Q2, is with respect to the source of the electric force, charge Q1. This vector r is just the difference between the two position vectors r2 minus r1, where, as in the gravitational case, we would get the same vector r for a different choice of coordinate system. Now, with vector r in hand, we can define the corresponding unit vector r hat, which we will use shortly to specify the direction of the electric force. Now let's describe what we need to know to specify the magnitude of the electric force. This force arises between any two objects, each of which has non-zero charge, so we would expect the charges Q1 and Q2 would come into play. Experiments and observations tell us that the magnitude of the force is directly proportional to the magnitude of the system charge Q2, as well as directly proportional to the magnitude of the charge Q1 in the surroundings, the source charge. Experiments and observations also tell us that the magnitude of the force depends on the distance between the two charged objects. Specifically, the magnitude of the force is inversely proportional to the square of the distance, where that distance is given by the magnitude of the vector r. We can combine all this together in a statement which says the magnitude of the force is proportional to the product of the magnitude of the charges divided by the square of the distance between the charge objects. The words "is proportional to" means that there is some constant which we'll call 1 over 4 pi epsilon 0, such that the magnitude of the force is equal to this constant times the product of the magnitude of the charge divided by the square of the distance. Now, 1 over 4 pi epsilon 0 is a universal constant, which has the value shown here in the SI system of units. Now we can write down an expression for the full vector electric force as the product of the magnitude and the direction. The magnitude we discussed completely, but the direction requires a bit more explanation since, as we mentioned earlier, the system could be attracted to or repelled by the objects in the surroundings. The direction of the force is determined by r hat multiplied by the sign of the product of the charges. In other words, if Q1 and Q2 are like-signed charges, then the product of Q1 and Q2 is positive, so the direction of the electric force is in the same direction as r hat. This makes sense in this case because our system charge Q2 is repelled by the charge Q1 in the surroundings. However, if Q1 and Q2 have opposite sign, then the product is negative, and so the direction of the electric force is in the direction of minus r hat, which makes sense in this case because our system is attracted by the object in the surroundings. We can write this more compactly by dropping the absolute value bars from the product of the charges. The sign of that product multiplied by r hat will always give us the correct direction. This expression for the electric force is called Coulomb's law and is rigorously correct when both our system and the object in the surroundings are point-like. That is, the spatial extent of the charges is small compared to the magnitude of r, the distance between them. However, it can be shown that if one or both of the charges are spherically symmetric, that is, each object can be thought of as being built up from layers of hollow shells, concentrically nested one inside another, like an onion, where the charge on each shell is spread uniformly on the shell, then Coulomb's law still applies as long as we use the center-to-center distance between the objects. As a final note, you'll recall that we could also build up concentric hollow shells of uniformly distributed mass and get much the same result for Newton's universal law of gravitation. However, don't fall into the trap of thinking this is a general property of fundamental forces. For other forces with a different dependence on distance, we can't treat a spherically symmetric distribution of material as a point in the center of the sphere.